about systems, and actually one of my major objectives here is, the audience here tends to be, divided by people who work on embedded systems and a few people who work on servers, and my objective is to try and corrupt as many of you as possible who work on embedded systems to take a look at servers and cloud. I'll try to keep the talk to no more than 45, 50 minutes, so we have a little bit of time for questions. But if something comes up in the middle that you want to ask about, feel free just to interrupt me. So the first thing, is just looking at systems in general a little bit. By the way, can you hear me in the back? Because I kind of like to walk around, but I don't want to do it if you can't hear me. So this is a particular chart from SanDisk, but you'll find lots of charts like this, and it's pointing out that the I/O and in particular storage and network is growing at rather a fast clip. And what I'm going to do here is look at some of the technologies underneath it, and I'll spend some time on storage. And that will then hopefully motivate some of the changes that we're making in our servers. So, what we use in most servers to get to storage and network is PCI Express, as I assume you well know. It's been on a clip of a new standard, every 4 years or so. Actually, the PCI 4 standard was done in 2015, so 5 years. And I know it says 2.5, 5, 8, 16, but it's actually because of the encoding that's used, it's roughly a doubling in each generation. So from a, if you overlay that with how the network, and here it's showing bandwidth per cable and storage, and there it's showing bandwidth per device. You see that in spite of a pretty healthy rate of improvement with PCI Express, the rate of improvement, and here, the absolute value of these curves is not really important. It's the slope of them that matters. And you see indeed that these have still a somewhat higher slope than PCI Express. If I take an IBM perspective on this, to us it looks a little bit different. We actually on Power 7, and that's not necessarily something to be proud of. We were still stuck on generation 1 PCI for the first iteration. Then introduced the second generation Power 7 Plus, P8 in 2014. We were on generation 3, and for P9 we've said that we'd adopt Gen 4, and we also said that P9 is slated for 2017. So that's actually introducing a next generation every 2 years or so. Now you might wonder, why, that seems really quite odd, right? To have a standard every 4 or 5 years, and then IBM, adopting this at a rate of every 2 years. Well, the reason really is that up until here, we relied on our own custom interconnect in servers, and then we would have I/O expansion drawers and things like that, to get to I/O. So it's really an adoption of IBM of this commodity technology that makes it look like this. And then if you plot that curve against the other ones, you see that more or less keeps up. So you might think, okay, well, that's pretty good. It's a bit of a question of whether we can keep this rate up, but at least up to Power 9 with PCI Gen 4, it should look pretty okay. Well, maybe not. So let's look a bit more at storage. So with storage, we've been on standards that are a little bit different than the PCI standards, but also spaced apart, roughly that same 4 years or so, right? So, that means that the number of PCI lanes that you need for a storage adapter that drives, some number of devices stays more or less constant. So things work not. However, and this is probably too small for you to read, but I'll explain what it is. This is a little table, it happens to be from 2013. And what you see here is things like hard drives, SSDs, and then, you know, most of these are sort of in the range that you expect. And then at the bottom there is a PCI storage device. So I don't know exactly which one this is, but you know, back in those days, things like file and memory and so on, right, where you had flash storage on a PCI adapter were quite popular. This particular one, you know, was doing 2 gigabytes per second, and for read, and 1.3 gigabytes per second for write. So that's you know, that's rather a different way than going about it. And basically, what was behind it is that you know, unlike the disk technology, where it really isn't very easy to grow the bandwidth because you need more read heads and spindles and all that. With flash, it's intrinsically possible to drive, you know, a lot more bandwidth than we were taking out of these devices through, you know, 1 or 2 of these SAS lanes. So people jump to PCI Express. Now, what's happened between then and now is it's basically still the same kind of device. So a typical enterprise flash storage device, a PCI device, will be, you know, 3.2 gigabytes per second, which is maxing out 4 lanes of PCI Express. So that's not very different. It is what is surprising though is that the cost of these things has come down now to where it's more or less in line with what you expect to pay based on the amount of flash that's in them, right? So you see these things in the neighborhood of you know, $1 a gigabyte or even below if it's not enterprise. And that means that we've had a crossover for a long time in IOPS per dollar for flash versus disk, you know, by I think almost 3 orders of magnitude. But now we have a crossover in bandwidth per dollar. So it is actually, if your objective is to build a system with as much storage bandwidth as possible for the least amount of money, and the amount of capacity that you need is not your primary concern, you're best off buying NVMe flash. You wouldn't buy it at 3.2 terabyte a disk with something like, you know, 800 gig or so. And you can get 800 gig drives that come pretty close to that number. You know, with 4K block operations, you can get 800,000 IOPS out of this. An enterprise drive is spec'd, you know, in this PCI form factor to be a 25-watt max device. And, you know, access latency to flash is still, you know, close to 3 orders of magnitude slower than memory at 50 to 100 microseconds. It's actually, you know, in a multi-socket server context, you know, that it may be somewhere between 2 and 3. So let's say, okay, well, we take our typical 2U server. If you had designed in the past the 2U server for bandwidth, you might have populated it with 24 2.5-inch drives. And, you know, naturally now you're going to populate that with 24 NVMe drives. No sweat. Well, what does that do? It actually gives you 76.8 gigabytes per second of I/O bandwidth. Well, our Power 8, if I have a Power 8 dual socket processor, and we're very proud of the fact that we had 48 lanes of PCI per socket. You know, you don't find this on very many processors. In that system, I would need every single available lane of PCI to drive these 24 NVMe drives. And then, you know, there's other folks, I spotted this thing as I was Googling about for this talk that has 32 drives. You know, with the disks, we wouldn't like to do that because you still like to get some air past it to cool the processors behind it. But probably with flash, certainly if you have form factors like M2 and all that, something like that is even thinkable. And then this would be, 100 gigabytes per second and already be using more than the PCI that we have on PowerA. It would give you 76.8 terabytes, or say 100 terabytes in the thing up there if you use those 3.2 terabyte disks. And then, so I color this yellow because it's clearly kind of at the boundary of what we can do, today with a reasonable server. And then I wrote 90.2 million IOPS, 800.8 times 24. And that is a number that we will look at some more. And then, in addition to that, those 24 drives would take some 600 watts, which is also a hefty number. In some data centers, they like the whole two-socket server to burn, no more than 600 watts. so you might be, in some contexts, you might actually be doubling the power of the server, with this NVMe in it. And what I'd like to point out here is that, well, actually, we're beginning to talk about sort of memory class bandwidth. I mean, 76.8 gigabytes per second is not as much memory bandwidth as we have in our power servers typically. But it's actually not an uncommon amount of memory bandwidth for a rack server. So we already see memory class bandwidth even before we have storage class memory. Okay, so let's see how this works out. So there are three ways, roughly, that you can decide to architecturally connect to this. So the first one is you can try to use flash as memory, right? And the physical way that you would do that is probably you try to use something like a flash DIMM. So in that case, your flash sits in real address space. And this is actually a problem. So if you have any hope of doing things like near memory compute, and you want to build accelerators or some kind of a transformation close to that memory, then that accelerator has to, it has to be able to use real addresses. And the only things in your systems that are allowed to use real addresses are things that have the highest level of privilege, hypervisor or OS level privilege. So I've seen a number, also in IBM, we've designed accelerators from time to time without an address translation unit on it. Every time we've done that, we've come to the conclusion that really the only way to use that accelerator is by the OS or the hypervisor. Right? So if you want to have near memory compute that's actually usable, by an application, you shouldn't do this. You cannot do this. Now, of course, you can, pin things and make effective equals real and all that, but now you're defeating, the whole virtualization capabilities of your system. So not an attractive way to go. Also, this is really not attractive if the latency is high, right? So a typical way of operation that you might see is, you have a read to such a thing as a flash DIMM. And by the way, I don't mean the flash DIMMs where the flash is there to provide a backup of the memory in case the power goes down, right? Those have typically as much flash capacity as they have memory capacity. I mean the ones where you say have an order of magnitude more flash capacity, and the DRAM that's sitting on these flash DIMMs is just, so that you eventually can read from DRAM, which the protocol is written for. So you access this device with an address that isn't already cached in the DRAM, and then it has to initiate a transfer from the flash to the DRAM. That takes a while, so you need a later synchronization with the requesting process to get it there. And that synchronization is again a very heavy and expensive operation. So again, not a good way to go. So I'm not saying that these kinds of things will not ever be successful, but I think that they really depend on the protocol being matched to the latency of the non-volatile storage that you use. So when you really have storage class memory with much lower latencies, this may be reasonable as a memory device, but it's still not a good way to go if you hope for near memory compute. So the second way is to attach it in I/O space, right? And that's the way it's typically done, you know, with these NVMEs and so on. You still have a problem in that, you know, you're a little bit better off than in the case of memory because there is translation in between, but it's I/O translation. So the I/O device only has access to things on the host side if that mapping is guaranteed not to change, right? So if you have an adapter talking to a buffer on the host side, that buffer has to be pinned, right? So that because the adapter wouldn't know if the OS, you know, otherwise moves it around. And because of this, because you know you obviously don't want to pin all of your memory in the machine because that again defeat virtualization. It usually means an additional copy, right? And it also means a synchronization between the adapter and the host application. So the adapter might put something in a buffer, and the application might pick it up from the buffer, for example. You know, a typical stack that you would go through with I/O might mean that a reasonable number to expect is something like 50 to 100,000 IOPS per core. Now remember that 19 million IOP number, right? So we could be talking about a few hundred cores there, right? That's a problem. So the third way to attach is through the SMP bus. You know, there we have full access to all system resources. You have the best support for offload and near memory compute. We can make use of the most efficient synchronization mechanisms, right? Designing an SMP is really where we force ourselves to come up with the most efficient synchronization possible. You know, including such things as being able to, you know, complete locks in caches and other things. And you know, the adapters that are attached in this way can interact with other adapters that are attached this way without even touching the CPU. And I'll talk a little bit more about examples of this. So for this reason, you know, I've been a proponent of coherent attach. So let me go through what we've done in IBM, and this here is actually a first example that this follows that first model, you know, of a memory type attached. So we've had a project that has been something that we did, you know, as a prototype. This is not a product. But in our Power 8 processor, we can actually provide up to 230 gigabytes per second of memory bandwidth for each socket. And the way we do that is we have buffer chips, eight buffer chips per socket. And normally, you know, we integrate this a few different ways. Sometimes we put a buffer chip on the motherboard, and then you just see standard DIMMs plugged into the motherboard. Sometimes we have a riser card, you know, with the buffer chip on it, and then you see standard DIMMs plugged into the riser card. And sometimes we build these DIMMs that we call CDIMMs, and they're called CDIMMs because the buffer chip is called Centaur, so Centaur DIMMs, where we put the DRAM chip on an IBM custom DIMM, which is the highest reliability, but of course, you know, the volume of these CDIMMs is not the same as the standard DIMM, so they're a bit more expensive. So what we did is we created a CDIMM with an FPGA on it, and then some you know, some sockets on the other side, DIMM sockets that we could attach stuff to. And we run the exact same protocol here, which we call the DMI protocol, you know, to that card. So this card is called Contuto. We showed it in April at the Open Power Summit, and it's one that we've been experimenting with such things as you know, different kinds of you know, non-volatile memory technologies, and also we've been experimenting with near memory compute, but for the reasons that I mentioned earlier. You know, I don't think it's very likely that we could, you know, commercialize something, at least in a server context for this. Maybe as an embedded device, such a thing would be possible. It certainly is attractive you know, the 230 gigabytes per second of bandwidth that you could have off of a single socket you know, is our best bandwidth number in the system, right? So for that reason, it is an attractive case to attach. Now, you know, as you can tell, I have a bias towards you know, coherent shared memory, which actually goes back to the cell processor, of course, right? The SPEs, you know, had the same view of system memory as the power ports did, even if they used a different mechanism to access it. So what we did on, you know, we built a prototype on Power 7. We introduced it as a product in Power 8, and what you have there is it's an SMP connection, but we put most of the burden on the CPU side to make it easier for people to design something that could attach to this coherent bus, but they wouldn't have to be confronted with all of the you know many state protocols of the coherent attach. A consequence of that, by the way, is that this is always a coherency endpoint, right? So you can't have another, you know, SMP link coming out of that device because it doesn't see enough of the protocol. So many things like snoops are handled by the piece that's implemented inside the Power 8 processor. It keeps a directory of everything that's held in the cache on the attached device, which can be an FPGA, but it can be some other kind of adapter as well. You know, Mellanox has been working on a CAPI attached communication adapter, for example. And then we also provide you know, a unit that we you know, if you're going to design an application that leverages this, you include this, what we call the service layer, in your design in the FPGA. So in that service layer, we have the translation, we have cache, you know, I think we instantiate some DMA engines, things like that. And then on the other side of that, you have a load, store, put, get interface that sort of looks the same as what you know, the way a processor core, say, would view the rest of the memory, right? With the caches and everything. So a colleague of mine actually describes this kind of like a hollow core, right? So you get a core with the, you know, bus interface unit with the L2s, with the address translation, all of that stuff, but everything except the core itself.
Peter, how would you compare this against what the Intel Altera part is doing? What is the basic?
I think the principle is the same. The principle is the same. You know, their physical integration is a little bit different. I think, you know, quite frankly, I think we're a bit ahead in terms of integration with like things like Linux releases, right? So currently, you can pick up any Linux distribution, and this stuff, you know, just works.
So do you have a notion of a basic cache block size that is the transaction unit on the bus?
Yeah, so because we really wanted to make sure that our, you know, that if I was going to design another Power 8 core over here, right? I don't want it to look architecturally, I want it to be identical, right? Which means that, for example, you know, if I have a locking mechanism that's based on a granularity of 128 byte, you know, cache lines or something like that, I really, you know, I'm not saying one could never compromise, but to first order, you know, whenever I was asked the question about this, my answer is make it the same, make it all the same, right? Don't invent new ways of doing SMPs, don't invent new ways of doing synchronization, make it all the same. I want an application that does a function call, right? Not the whole layout in memory, the synchronization, everything. You shouldn't know, you know, whether there is a CPU core executing instructions behind it or a piece of hardware, you know, running something through a bunch of gates. You should not know the difference. And if you have to know the difference, then I think the complexity of doing acceleration will explode on us, right? Because that means that when you do, you know, software design, you're going to have to start worrying about which kind of accelerator is and is not allowed, to execute that particular function. This is, and you can't have, dynamic environments, right, where you're running a program and, during runtime you say, oh, okay, I have this one is available, or this one is available, now let me use it. And then the next time you go do the same function call, maybe it's not available, right? You do it differently. I want it all the same and flexible and dynamic. We are mostly there. I'd say we're more than 90% there. We're not 100% there, but we're, very much, in that direction. Thank you. That was a good prompt. Okay. So what we've done with that in a storage context is we used it to make an adapter that would attach to Flash. So on the one side of the adapter we have the CAPI interface. On the other side we have a block device. And we can now expose the block device to a user process. So the user process can do a block move, somewhere into memory. We could have even, built a system where if you would have typed top, I think these boxes can hold, like 96 terabytes or so these days, that you would have seen 96 terabytes, but we didn't, the whole Linux stack and everything, and how it handles, pages and swapping things in and out. We didn't think that was going to be successful. So we do have a separate space, for the block-based memory. And what the user process does is it moves things in and out. And then we have a number of different APIs. We have one that's based on blocks, another one that's based on blobs, i.e., things of arbitrary size. And then there are others that have built things on top of that. And the first one to do so was Redis. That they built a key value store on top of these APIs that I identified. So the net effect of this is that we're taking, that stack that goes through the logical volume manager and the device drivers and all that, which I think was something like 20,000 instructions or so, down to a few hundred. And you can make that almost arbitrarily small because the adapter, like I said, is a fully capable thing. You could even put a processor on it, right? So the only fundamental cost that you have is the same cost of handling a transaction over to another core to handle and complete it, and then pass control back to you. All right, and what you then see is that the number of transactions that we can perform on a hardware thread. So here I'm not talking about a core, I'm talking about a hardware thread. Is very dramatically increased. Your latency also improves, and not on this chart, but quite important in a number of contexts, is because we don't go through a device driver. We don't get affected by such things as OS jitter, right? Operating system having to handle other things. So the jitter of these operations is much better than you would see in a normal way of attaching flash. Right. So physically, again, the only thing that we change is instead of using a standard, in this case, fiber channel adapter, we use one of these CAPI-based adapters, and a bunch of FPGA programming. So one of the things we did more recently with an intern that we had from Binghamton University, who also continued to work with his advisor, Patrick Sandier, is we used that Cassandra. Cassandra is a bright optimized skill store, and the point of this chart is that if you it's about having strategies for write logging, right? So in a fully transactional database, every transaction gets logged immediately, right? In no SQL store, what you do is you decide to bunch them up and commit them every once in a while, or every certain number of transactions. So if we do no write logging at all, then you might get this performance. And what we could see is that when we use a CAPI-based interface, we can do write logging actually every single transaction and get very close to the no write logging case in terms of performance. Whereas if you would do that the normal way, your performance would I mean, this is not reasonable. It's not what it's designed for, right? I mean, it's not meant to be a transactional store, but we can get very close to that kind of functionality with performance that's very close to no overhead at all. A company, Neo4j, picked this same API up for a graph database, and they were enthusiastic about it, claimed the 10x advantage. And we've been using it for Spark. So, I explained a little while ago that we can build these systems where the amount of bandwidth that we get out of this flash really begins to look like memory, right? So the question was, okay, well, if in Spark we try to replace memory with flash, because Spark is an in-memory version, right, of Hadoop. And it's nice in that it's very fast and you can do transactional things and so on. But of course, memory is a whole lot more expensive than disk for capacity. So we said, oh, well, maybe we can use flash and reduce the amount of DRAM-based memory that we need in the system. So this is just a prototype, an initial study. We had a certain application, and then we artificially constrained the memory, and we'd see our runtimes, go up, right? As when we constrained the memory, eventually we had to flush more and more of the RDDs, out to storage. And then we introduced this CAPI flash, and we came to the conclusion that we could reduce the memory size, a factor of 4 times more without much impact on performance. And this was based on the design with the the single adapter going to the flash-based drawer, the IBM flash system. And I'll show you that we can do other things that are even more encouraging. So this is a more recent incarnation of the same idea. It's a card designed by Nalatech, and it has I think KU 60, I think, FPGA, Xilinx FPGA here. And instead of coming out, well, you could do this thing, and you could use it as an adapter to an NVMe device or so, right? This is little M2 form factor cards, so you could go from there, into a cable to something like an M2 device that sits in the front. But you can also take an M2 stick, right, and just plug it right into the card. And I think you can get you can get a few terabytes of flash, on a neat little. It looks just like a normal NVMe card, except it's a CAPI NVMe card, right? Which has the benefit now that we again can have a lot less overhead per transaction. And Alan Cantle from Nalatech, tells me that there's actually still room available in that device, if you want to do some near flash transformations. My favorite is a GZIP that we developed some years ago that's actually fast enough to keep up with these kinds of transfer rates, and then we could just it takes a few microseconds to GZIP compress or uncompress a page, right? And that's small enough to put in line with flash without really adding much latency to it at all. Okay, so I looked at storage in some detail. There's a parallel story for networking that I don't really have time to do at the same level, but it's probably if you're watching this, it feels like the transition from 10 gigabit to 100 gigabit per second in data center context, if anything, might be faster than the transition from 1 to 10 gigabit per second it felt like data centers were forever hanging on to 1 gigabit type infrastructure. And you know, I think part of the reason is that we are moving more and more away from spindles to things like flash, which means that, and we're moving to compute paradigms like Spark, which are more in memory based, which means, you know, that the pressure on the network is growing a lot more rapidly than in the past. Another thing is that we are making the transition to optical cables. I mean, yes, we can build a 100 gigabit copper cable, but they're kind of a little bit unwieldy, you know. And when you're doing a longer run, you really like to run fiber. I think really once we, you know, a lot of these things are on cost volume curves, right? So when we really start to run fiber a lot more, you know, the price will come down, and there's a sort of a new window that opens, right? Once you're on fiber, we have a lot of room for bandwidth growth, you know, even beyond this. And here too, just as in the storage case, there are advantages to having a coherent attach, right? So if I want to build, say, a distributed key value store, right, I can have a network adapter that you know, that picks up the request, gets it over to a network adapter somewhere else, and it can reach into the system, reach the CAPI attached you know, storage card, pick the data up from it, you know, send it back without the CPU or the OS or anything even ever being touched, right? So it's nice to also have CAPI attached communication. And then, you know, just about every time I give a talk like this, you know, I've had this chart up, which is about compute, you know, and the need for us to, you know, to go beyond the efficiencies that we can get from multi-core, you know, to heterogeneity. So I'm not going to repeat that story here, but obviously, you know, CAPI attached compute is kind of where we started. So the conclusion so far is that, you know, I hope it's clear to you that, you know, we have a lot of pressure on bandwidth. We have, I hope I've done a bit of a reasonable job motivating why we'd like to be coherently attached. And so the question is, what are we doing about it? So the first thing is we're not going it alone. So we have the Open Power Foundation, and this kind of CAPI coherent attached technology is a big part of that. And you know, as you can see here, you know, that foundation is growing. The second thing is you know, you have to tell people what you're going to do. So we did that at the Open Power Summit, and there's you know, two processors here, the Power 8 plus NVLink, which I'll talk about a little bit next, which introduces a lot more bandwidth to, in this case, a GPU, which is supposed to come out later this year, and then Power 9. We started to give some details of the Power 9 chip that we call the scale-out chip, which is targeted at data center. And I'll give you more details about that as well. So then, you know, of course, the CAPI, and I already talked about that. And then increased bandwidth. So this is this Power 8 plus NVLink. So normally you attach GPUs also through a PCI interface. This is doing, you know, this is not, I think they're at sort of page level coherency at this point, so it's not the same as a CAPI interface, but it does have tremendously more bandwidth than a PCI interface. So this NVLink interface goes up to, I think, 80 gigabytes per second per direction, which is about 5 times what you would get from a PCI Gen 3. And when you see 5 to 12 times, I think that's also a bit of a forward reference to what might happen with future generations of that interface. so there's a processor coming up, and we showed some some systems that have this, where you might have. So in the previous picture, you saw a CPU connected to two GPUs. So these GPUs, instead of being in a PCI form factor card, they actually use the two little connectors here. These are cards that span those two connectors, and if you put a heatsink on top of it, it looks something like that. So it looks roughly like a socket, but it's actually this pair of connectors. And this is another card from Inventec that might be more of an open compute type form factor. Not 100% sure. There was a system that Google and Rackspace are working on called Zaius that also said that they would use that kind of thing for Power 9 in that case. Okay, so really grow the bandwidth, and then the next one is, well, we would actually like to have all of that bandwidth, and we would like to have the coherent open interface. So this is what OpenCAPI or CAPI 2.0 is about, and in Power 9 we will have a set of IOs that just like we're using the PCI Express physicals to run either the CAPI interface or a PCI Express interface in our systems, right? So it's a configuration switch. We could use a set of 25 gigabit per second physicals transmission lines to get to various kinds of accelerators, but maybe not the same protocol. And we haven't disclosed what that bandwidth would be, but I think it would be logical to expect that we don't go backwards. So that's attractive. Now you can have coherent acceleration with something like an FPGA at a bandwidth that is, I would say, memory class type bandwidth. So I find this this quite exciting, and a number of our open power partners have actually begun to show things that leverage this. That I find really interesting. Okay, so the last thing I wanted to cover is so there's a lot that we're kind of throwing at people, and we would like as many people as possible to be able to access this. Not only the universities that are sort of rich enough to buy their own systems and so on. Right? So we set up, working with the open power partners, and also working with TAC, which is NSF funded. We set up a number of cloud resources that people can use. The first one here is called SuperVessel, and the slides will be available, so you can read the details here of how you can get there. But basically, on SuperVessel, you can get a VM, and you can get an FPGA, and there's resource there to compile your own images for that FPGA and just try this kind of stuff out. When you have something, you can also publish it for other people to use, and there's a dozen or so applications that are already out there. Some developed by IBMers, some developed by partners, and everything from neural net type things to genomics related things to sequence matching to fast Fourier transform, etc. And then the other one is Fabric, which is Derek Chu is well known from his efforts at Microsoft. I think is the main instigator of this. It's situated at TAC. I think access to it may be a little bit more restricted. I think it's strictly academic, right? So this is meant for I think open source type projects. But you actually get a little bit more resource. You get essentially a full node to play with the FPGA. And there's some links to that here as well. And both of these are are free to use. And then IBM also just recently started a programming contest, so I put that slide in there as well. Okay, so I think that is my prepared material, and then I hope to leave some time for questions. Thank you.